So here's a formula, right? The sum, S, capital S, of n terms of this arithmetic sequence, right? 1, 3, 5, arithmetic, what's the common difference? Looks like it's 2, right? The nth term of the sequence is given by this formula, 2n minus 1. If I added up the first term, right, just meaning 1, then the sum is 1. If I add up the first two terms, 1 plus 3, the sum is 4. If I add up the first three terms, 1 plus 3 plus 5, the sum is 9. So do you see a pattern here? S1 is 1, S2 is 4, S3 is 9. What's going on? Taylor? They're all squares, not square roots, right? They're all squares. So we could hypothesize that, in fact, we have a formula here that the sum of n terms of that sequence could be written as n squared. Right? If we use that formula, what would we think is the sum of the first four terms? Yeah, you would say S4 equals 16. Well, is 4 squared, which is 16. Okay, well, that would be S3, that would be 9 plus 7, which is 16. So it works. So, we could say that this formula, for those numbers that we can check, works. But how do we know that it's going to work for all n? I mean, it seems like it must because it works for these 4. But you don't always know that. And in the text, on the first page here, they give us a formula which is actually related to prime numbers. And it's a formula for generating prime numbers, and it's called Fermat's number. A Fermat number is 2 to the n power plus 1. And back in the day of Fermat, which is like in the 1600s, he showed that it worked for n equals 0, and it works for n equals 1, n equals 2, n equals 3, n equals 4. The thing is that the numbers got so big after that they didn't have the calculating power to actually figure out. Well, they could figure out what the number is, but how could you check to see whether it had any factors? There was so many factors to check, and you couldn't do it. It took like 100 years for somebody to actually prove that, you know what, if you put in n equals 5, it doesn't work. So it looked like it worked for the numbers they could check reasonably, but it didn't work for the next number. So how do we know that this formula will work if for all n? What if I plug in, 1,000,000 and it doesn't work? So that's why we need a method like this to help us show that formulas are true.